On October 29th, 3I/Atlas will disappear into the sun's glare, aligning with Loeb's theory that this enormous, high-speed interstellar body might perform a covert adjustment to bind itself to our solar system permanently. Authorities describe it simply as a temporary comet. However, initial observations challenge that narrative. A core potentially spanning 20 kilometers and tipping the scales at over 33 billion tons, all without detectable non-gravitational forces amid intense gas emissions. Should Loeb prove correct, this could mark the debut of an interstellar guest that sticks around, leaving us blind to its pivotal transition. What secrets will unfold in that solar shadow? And whose perspective will prevail once Atlas resurfaces? That date carves a sharp divide in time. Then, 3I/Atlas enters the overwhelming zone trailing the sun, blocking all terrestrial observatories. The alignment is unforgiving. Our world, the star, and the comet aligned linearly, with Earth stuck on the dazzled end. Over almost 6 weeks, the biggest interstellar entity we've ever spotted will travel out of sight, its trajectory and potential shifts concealed from observation. Far from a mere timing hiccup, this obscurity ensures that key events, like perihelion, the sun's nearest pass, or any orbital tweak, occur without scrutiny. The Earth-Sun span measures roughly 150 million kilometers. During conjunction, Atlas glides slightly farther out at 1.36 Australian dollars. No surface-based scope can tease its dim light from the sun's blaze. Orbital instruments such as Hubble and JWST must stand by too, their safeguards activating against solar proximity hazards. Consequently, information dries up from late October into early December. Position logging, light spectrum studies, and even routine luminosity checks all cease. Slim chances lie with select sun-watching spacecraft and coronagraph devices, geared for solar flares, not remote icy wanderers. Their detection range and snapshot rhythm struggle to capture something as subdued as Atlas. For the majority of skywatchers, visibility ends precisely when the plot thickens most. Unresolved debates on natural departure versus deliberate retention, on icy rock versus artificial relic, linger in this imposed quiet. Time presses on, and the crucial reveal will happen unobserved. Loeb zeroed in sharply as the first light readings arrived. The preliminary diameter for 3I/Atlas, 20 kilometers, struck like lightning. To put it in perspective, 1I/Oumuamua clocked in under 0.25 kilometers. 2I/Borisov, the prior interstellar comet, might have reached just 1 kilometer. By contrast, Atlas dwarfs them by a full magnitude beyond what detection efforts anticipated as an opener. This wasn't speculation. It stemmed from the body's luminosity, adjusted for range and sunlight incidence, then compared to established comet shine properties. At a brightness exceeding magnitude 12, absent a thick, light-scattering haze to inflate the figure, the implication stood firm. The core must be substantial. Loeb's doubts stemmed from the figures. Detection forecasts suggest that for each big interstellar arrival, hordes of tinier, dimmer ones ought to have shown up before. Efforts like the Atlas Survey, Pan-STARRS, and the Vera C. Rubin Observatory sweep the heavens nightly, calibrated to snag these swift solar avoiders. Still, the initial pair were modest. Then, abruptly, a behemoth emerges. Per any distribution formula, the probabilities stretch credulity. Assuming the dimension sticks, either vast swarms of lesser fragments evaded notice, or an unusual, baffling factor intervenes. Here kicks off Loeb's case. Spotting a 20 kilometers interstellar traveler so early after the pioneers bucks the scaling rules that drive contemporary search strategies. The statistical red flags blared not over Atlas's visibility, but its immense size clashing with astronomers' assumptions of the cosmos's inventory. For Loeb, that lone metric, 20 kilometers, emerged as the prime, stark irregularity amid mounting oddities. A weight of no less than 33 billion tons now cements 3I/Atlas in the annals. Derived from motion simulations and the object's steady glow, it overshadows all prior verified interstellar finds. But the contradiction starts right there. Even with robust venting at 100 to 150 kilograms per second, chiefly from CO2, no non-gravitational push registers. In comet dynamics, this mirrors the thruster dilemma. Gas ejections serve as impulses, nudging the core faintly from its gravity-only route. Standard comets bear traces of even mild outbursts in positional logs, a gradual shift, a gentle bend from strict orbital pull. Yet the Minor Planet Center's worldwide archive, with more than 4,000 location points, detects zero such offset for Atlas. The ceiling on its non-gravitational, the observed acceleration of this object, falls below 15 meters per second squared daily, a figure so minimal that only an extraordinarily hefty body could exhibit such stability amid its detected outbursts. The data intensifies the puzzle. Consider the recorded output of gas, multiply it by the expulsion speed, and divide by the projected mass. The anticipated thrust effect ought to show up in observations, barring a core that's not merely enormous but exceptionally compact, or emissions that cancel out symmetrically across every axis. Computer models using Monte Carlo methods explore all reasonable variations in core dimensions and compactness. For cores under roughly 5 kilometers in diameter or sparser than 1,000 kilograms per cubic meter, the calculations fail. Such emissions would have propelled Atlas far from its forecasted route ages ago. Solely a colossal, rigid entity aligns with both the photometric and orbital data. Other ideas, such as opposing jets or a cluster of feebly connected debris, demand exquisitely calibrated forces and unlikely configurations. Conventional theories falter in harmonizing these figures without resorting to rare coincidences or contrived excuses. To Loeb and his team, this represents more than an oddity. It's a compelling prompt. With confirmed mass and negligible thrust, possibilities beyond natural origin stay ajar. Astronomy relies on vast datasets. For every behemoth like 3I/Atlas, forecasts suggest the cosmos ought to teem with thousands of dimmer, lesser interstellar drifters. The reasoning is straightforward. In all documented asteroid and comet populations, tiny items vastly outnumber the giants. Assuming detection systems function properly, initial interstellar finds should consist of the smallest specimens, those overwhelming the large ones by factors of magnitude. Yet the findings contradict this. The Pan-STARRS survey, the Atlas Array, and soon the Vera-C. Rubin Observatory have combed the heavens for years, cataloging millions of sightings. Their precision now catches objects mere tens of meters wide, provided they zip by swiftly enough in their records. The initial pair of interstellar objects, Oumuamua and 2I/Borisov, matched expectations, compact, subdued, and barely detectable. Suddenly, Atlas emerges, spanning 20 kilometers, weighing at minimum 33 billion tons. It blazes well beyond spotting limits. No flock of tinier relatives, no steady increase in scale, just an abrupt statistical jump. Experts in population dynamics crunch the stats. Should 3I/Atlas be representative, searches would have uncovered hundreds or thousands of minor counterparts already. But the tally stands at 3. Reports from Pan-STARRS and Rubin teams highlighted this discrepancy in private notes, cautioning that spotting a colossus prior to its petite peers carries odds slimmer than 1 in 10,000, per certain calculations. The size-frequency-power law, central to distribution patterns, seems shattered. Perhaps the cosmos conceals a horde of obscure, hard-to-spot entities, or Atlas stands as an aberration appending all predictions. For anomaly hunters, this transcends mere interest. It's an indicator that core assumptions in the data ring false, and 3I/Atlas's narrative is already reshaping paradigms. Path projections for 3I/Atlas show a route skimming the ecliptic plane of our solar system, inclined by merely 5 degrees. For an intruder from beyond, such conformity is highly unusual. Even native comets and asteroids trace paths that veer and coil across the local stellar domain. A haphazard arrival from afar ought to cut at a steep incline, its direction molded by the turmoil of remote stellar realms. Yet Atlas sails nearly flush with the planetary plane, navigating a lane typically claimed by indigenous objects. Deeper scrutiny amplifies the oddity. In the lead-up to perihelion, Atlas chains a string of brushes with key worlds. On October 3rd, it passes 29 million kilometers from Mars, a proximity that's a whisker by cosmic yardsticks. The pattern persists. Subsequently, its course nears Venus and Jupiter, amassing a series of planetary grazes uncommon beyond scripted probes. Specialists in orbital mechanics compute the figures and deem the cumulative likelihood of such a bulky, swift traveler navigating this exact sequence microscopically slim. Each world's close shave is improbable on its own. Chaining 3 slashes the chances under 1 in 1,000. This synchronization goes beyond quirkiness. The low ecliptic trajectory positions Atlas ideally for gravitational tugs. Theoretically, every planetary pass might adjust its velocity or curve its arc. But the deeper fascination concerns how these layered interactions prime the perihelion phase. The path feels precisely calibrated, as though crafted to optimize prospects for a striking pivot by the sun. For investigators probing the line between chance and design, the orbit stands as a mute testament, posing dilemmas that raw figures can't resolve. The initial photographs from the 3 observatories monitoring the 3I/Atlas comet revealed something unexpected. Rather than the anticipated tail, an intense forward radiance overshadowed the side facing the sun. This luminosity withstood all adjustments for motion blur or equipment glitches. Analysts examining images from Gemini South and the VLT scrutinized the information intensely, hunting for an instrumental cause, yet the imbalance persisted. As the comet drew nearer to the sun, the radiance diminished, and a typical tail started to extend outward, consistent with solar wind patterns. Certain experts dismissed it as a mere optical illusion due to perspective, while others viewed it as evidence of genuine transformation. Maybe the surface crust had cracked or a rapid eruption of subsurface activity had occurred. Researchers studying spectra turned their attention to the comet's composition. The JWST's NIR spectroscopy, squeezed into a tight time frame prior to solar conjunction, detected a volatile mix that contradicted standard models. Carbon dioxide surpassed water by almost an 8:1 margin. Among solar system comets, water usually reigns as the primary volatile. This unusual proportion suggested a core either kept in frigid isolation from its interstellar origins or encased in carbon dioxide ice. Verification groups advised restraint, labeling the outcome tentative pending additional observations to validate or refute it. Hypotheses proliferated. A few invoked a carbon dioxide shell protecting a water-abundant core, while others suspected interference or flaws in the analysis. Discussions erupted in late evening Slack conversations, with each group staunchly advocating their viewpoint. Then, during late September, a vivid green glow suddenly permeated the coma. Observations from both hobbyist and expert astronomers confirmed the alteration, linking it to C2 or CN molecules glowing under solar UV radiation. In typical comets, the green hue emerges close to perihelion, but for this one, it showed up ahead of schedule and more intensely than forecasted. This shift in color sparked fresh inquiries into the arrangement of volatile ices and the comet's exterior makeup. Each irregularity, visual, compositional, and spectral, piled doubt upon doubt. As the comet vanished behind the sun, resolutions remained deferred, its essence caught between mere illusion and profound discovery. Avi's hypothesis rests on a fleeting interval that scarcely marks time on the universe's scale. At perihelion on October 29th, 3I/Atlas will hurtle along at close to 44 kilometers per second, an interstellar projectile curving a mere 1.36 astronomical units from the sun. For anything following a hyperbolic trajectory, this represents the singular instant when a modest velocity adjustment, a few km/s alteration, might shift it from fleeing forever to being ensnared. The dynamics allow no mercy. To redirect from an outgoing interstellar course to a stable solar system orbit, Atlas would require about 8 kilometers per second of delta V applied precisely at closest solar approach. Less than that, and it speeds away indefinitely. Should such an intervention occur, it would go undetected. Solar brilliance overwhelms all ground-based telescopes. Superior orbital coronagraphs would still falter in spotting a dim, swift dot amid the sun's glare. Sensitivity thresholds for these tools range from magnitude 8 to 10, which proves too luminous for an object like Atlas amid conjunction. Consequently, any path deviation, outburst of material, or artificial propulsion would evade notice until the comet reappears after several weeks. The upcoming Mars encounter, only 29 million kilometers away on October 3rd, sparked momentary optimism for close-up views. Mission coordinators weighed the odds, crunching figures on size in the sky and visible magnitude. The math dashed hopes. From that range, a 20 kilometers body spans under 0.15 arcsec, below HIRISC's resolution threshold. Even treated as a mirrored, Atlas would appear too dim to capture. No details of the surface, no gas jets, no deployed probes. Mars' premier imager can merely observe empty void. For Loeb and his allies, this unavoidable obscurity serves as both irritant and advantage. If an operation unfolds, its traces will embed in the orbital path, ready for analysis once Atlas returns to site. Tom Statler, NASA's principal expert on small bodies, sets a firm boundary amid the speculation. It appears cometary. It exhibits cometary behaviors. It mirrors known comets in virtually every aspect. That forms the foundation. The prevailing perspective places 3I/Atlas, albeit uneasily, among the diverse, chaotic clan of ordinary comets. Peculiar mass, chance anomaly, quirky makeup. Comets defy neatness. Path oddities and close planetary passes. Serendipity amplified by cosmic expanse. Figures like Karen Meech and Xuanji Yi reinforce this position, citing observational biases, inconsistent detection records, and the erratic nature of isolated objects. To them, the onus falls on the unconventional assertion. Allo tackles the identical evidence from the contrary angle. He avoids a structured metric, yet builds his rationale by accumulating deviations, mass, dimensions, ecliptic positioning, planetary brushes, elemental profile. The tighter these traits align, the more compelling the rationale for scrutiny. In Elle and Joe's perspective, once a sufficient number of peculiarities accumulate, the prudent course is to intensify monitoring, particularly during an uncommon occurrence such as perihelion passage behind the Sun, which might obscure a pivotal adjustment. He avoids quantifying it, yet the concept is straightforward. As the catalog of deviations expands, approach the entity with the gravity it deserves. The upcoming key opportunity arrives in early December as Atlas exits solar conjunction. Leading telescopes worldwide will be geared up to examine shifts in its trajectory, spin, and composition. Come March 2026, with Atlas approaching Jupiter, another wave of observations will determine if its course persists as hyperbolic or shows alterations. The analytical approach focuses not on tallying irregularities, but on pursuing verifiable, testable forecasts. Should the path hold steady, the conventional explanation stands firm. If not, the discussion shifts to uncharted territory. At present, the sole assurance lies in awaiting revelations from the data once visibility resumes. On October 29, 2025, 32/Atlas will slip behind the Sun, halting all ground-based views right when Loeb posits a retrograde binding operation might secure it within our solar system. The object's approximate 20 kilometers diameter and minimum mass of 33 billion tons, paired with minimal non-gravitational forces and a carbon dioxide to water proportion close to 8:1, align with projections for a typical interstellar comet. Still, as things stand, nothing conclusively points to an engineered source. NASA's stance holds that comets often display erratic traits, leaving puzzles like the origin of its greenish spectral signature and the exact character of its path unanswered. Upon Atlas's reappearance in December, updated orbital parameters and molecular markers will deliver the ultimate verdict. In the interim, the imperative remains thorough scrutiny and candid scholarly discourse.